Talk about a mobile interferometer that we just tested at 2 a.m. this morning, mobile for the first time. We got some really great results. I'll show that. This started probably around February of this year when I ride my bicycle down to the 40-foot a lot, and I do a lot of SETI down there. I have my computer from home that I hook up, and I also have an interferometer at home that I keep there. But I had this wild idea as I was riding that straight road towards the 40-foot that I wonder if I could get a mobile element on that line and bring my correlator from home. Maybe I could use this as an interferometer. Now, I only get the time on the dish that you're looking at the sky, right? Short period of time. But I thought, well, if we could drive that, it might work. Well, for maybe 10 or more years, I've been interested in trying to build an interferometer that has a moving...
Did you get F5?
Pardon me?
So it displays?
Oh, yes, thank you. Oh, sorry. Sorry about that. Yeah, slideshow mode. Thank you thank you. Yeah, for 10 years or more, I've been interested in trying to make an interferometer with moving elements. It's a kind of difficult problem. And so I built a bunch of them, some long baseline ones with microwave linked over the years, but they're all fixed. They're fixed baselines. So I had this idea, and then in March I was at the Western Conference, and I just, in the breaks, I was saying, maybe we should try to make an interferometer at Green Bank. And Tom Hagen said, well, I'll make the mobile element for you. That was March. Well, this is great. So then Dayton rolls around, and he brings the mobile element to Dayton on the top of his car, Dayton Hamvention. And I was already planning to go, but definitely I'm going to go if the dish is going to be there. So then I transferred the dish to the roof of my Subaru, brought it to here, and with the help of people here, in like 20 minutes, we got it all set up static out there. So a month ago, I tested it static, and on Cas A. And then we tested it static again yesterday on Crab Nebula. But we hadn't done a mobile test. And that was this morning at 2 a.m. So we got some results. It came out very good, and I'll show you that. So what I'm going to do is talk about the objective, what we were trying to accomplish, what we were looking for baseline, how the baseline was going to change, that sort of thing. And I'm going to spend some time talking about how interferometers work. And I'm going to try to make it so we can understand it, and it's kind of coordinated with what we tried to do for this particular observation, which is Cygnus A, 2 radio lobe source. What the system is, the mobile interferometer, what we don't do, because this is a very simple system, and some future ideas, and then the observations, what we saw last night, or 2 a.m. this morning. So the objective is to build a mobile interferometer. We're going to first look at Cygnus A, dual radio lobe. I'll talk about that a little bit. The east element of the interferometer is the 40-foot dish. It's a transiscope, 180 degrees to north, so all we've got is this basically single fixed element with fixed pointing, actually, which is unusual for an interferometer. Usually they want to track the object. And then the mobile element is the antenna that Tom made, a 6-foot dish on a truck, and we're actually using Mike Holstein's truck, and I have the key to it right here. So, and the antenna is still mounted on it. So if I don't fall asleep, we could probably do something else while we're here. Okay, the signals are carried from the mobile element back to the correlator. It's an obvious problem, over coax. Okay. So I made up 1,400 feet of amplified coax, has loss of 90 dB. Put a bunch of I calculated how much length. I decided to go with 200-foot lengths with amplifiers in between them. And it turned out we only used 1,000 feet plus 100 feet that was fixed, or 200 feet that was fixed, so a total of 1,200 feet of coax. And it's laying in the field on the road there going out to the 140-foot right now, because we finished the measurement last night. I have a 125 megasample per second sampler. Talk about that a little bit. how I compensate for coax delay, because we got to get the waveforms have to fall right on top of each other for the system to work. This frequency is 1405 to 1445 megahertz. I have 2 bandpass filters that I put in the receiver at the jumper points where you can put your own filters. It samples for 0.73 seconds, so there's a dwell time. It's actually not a continuous sampling because it's all done in i7 multi-core. So I program all the cores in an i7 8 cores in a 4 gigahertz computer, but I get 160 milliseconds of integration time and simultaneously on multiple cores over the 40 megahertz range. And then the idea is to look at the delay taps, and I'll talk about a little bit about how that works, but the idea is you got to get the waveforms lined on top of each other. I'll show how that works in order to get these correlation peaks. And so there's a penalty paid when you want to look at a lot of different delay taps. And so this has a limited number of delay taps, and we had to figure that out. And so there's the Cygnus A observation. So this is Cygnus A. This is an image taken with a VLA. This was actually the first, I believe it was the first image taken when the VLA was built. That was it was essentially a long-term, I think it was all A, B, C, D configurations of the VLA. And it was taken at 5 gigahertz. There's a black hole at the middle of this, supermassive black hole. We can't see the galaxy in this image, but it's absorbing a very large galaxy. The distance between these two ends of this picture is about 6 Milky Way galaxies diameter across. The supermassive black hole is spinning, and as a result, charged particles and mostly electrons end up escaping from the black hole on the poles of the spin. I'm not an astrophysicist, so I'm just speaking from what I pick up. Those electron jets, traveling close to the speed of light, eventually can't keep going, and they pile up on each other. The matter piles up on each other. They end up breaking. And when they break and hit each other, they create extreme acceleration of charged particles, which creates extreme emission of radio waves and other photons. So basically, anytime you move an electron, you get a photon out of it. Anytime, not move, but accelerate. That's how antennas work. So those two are radio hotspots. Now, I didn't have 1400 megahertz image of this, of Cygnus A, so I guessed that these two radio hotspots at the end are fairly well concentrated, maybe also at 1400 megahertz. But that's still an unknown that I don't know from my investigations of the object. The idea was to get something that we could glean from that. So this is a image of the site. The 40-foot telescope is up there in the upper right. The interferometer baseline goes out towards the 140-foot telescope, and it's a straight line. Oh, I forgot, I skipped over this slide. This is the telescope here, and that's the mobile element, the 6-foot dish, mounted on a frame that we could easily lift up and put into the back of the bed of the pickup truck. Whoops. Oh, okay. Sorry if that, okay.
So how many feet of coax have you got on that thing right now?
1,000 plus 200. So we've got 1,000 if it's going out, and there's a big red marker out of the end that says do not go past this, or parts from inside the 40-foot room will start to be pulled out of the room. Okay. But it's, so that's 1,000, and then there was a 200. There's a 200 fixed that's on the antenna itself, which it's more convenient to have along, some coax on the antenna, so we don't have to get up to the feed to do things. So that gets attached together with 1,000 feet. And so, okay, so the way interferometers work is, let's imagine we have a single source in the sky, and the waves are arriving, the electromagnetic waves are coming in at us, and we have two elements. So, for example, we have these two parabolic elements that each have feeds on them, and what we do is we take we take the product of those two waveforms as they arrive, the product of the received voltage. This is one way to do an interferometer is you take the received voltage and you just multiply it by each other on the two elements. The distance between the elements is defined as the baseline. Now, the waves can come in, and they could come in, and we could be on a negative peak on the wave, or we could be on a positive peak. And you say, well, wait a minute, these look like really clean sine waves, plus, minus, right? But we're filtering 1400 to 1445 megahertz. So if you looked at that on an oscilloscope, you would see something that looks kind of like a sine wave, because you'd only be seeing the wiggles between 1400, 1404, and 1445. But the amplitude would be going up and down like this. So for the most part, it actually does look like this, with plus, minus in a nice uniform way, because it's a narrow band, but it has varying fluctuation in amplitude. Now what ends up happening is that it doesn't matter whether you have a positive waveform arrive on both elements at the same time, or the negative, or the trough. Both sides are going to integrate out and produce a positive value on the cross correlator. So I'm just using the term roughly called cross power, which is, it's the amount of power you would have if it was a single source and you're multiplying the voltage together. And now I'm only doing real calculations here, so I'm not doing complex. It's something for the future to look at. So, so you get the same output out of the cross correlator over time, regardless of how the wave is arriving with whatever phase. Now what ends up happening and this is just text of what I just said. So now what happens? What happens if it's displaced slightly? So it's not coming in straight in, right? Well, now we have the same situation we had before for the straight in case with a positive output, but then as soon as we displace it by an angle on the sky, we end up getting plus times minus, minus, plus, etc. And we get a negative value. So the output of the correlator is going between a positive and a negative value as the object is moving across the sky an angle. It's going up and down in phase like this. Okay? Now, how do we calculate the meaningful output of that sort of thing? Well, it turns out that the angle to the object and its motion across the sky is congruent with the angle of the baseline and the half wavelength of difference between the width at that particular frequency, at that distance. So baselines are, I'm using meters, but oftentimes they're converted to wavelengths when they're plotted in a plane called the UV plane, which allows this to happen in 2 dimensions. This is all one-dimensional right now, so what I'm talking about, but it extends to 2 dimensions. So what do? We calculate, now based on that sky angle for Cygnus A, the 2 strong radial lobes were 2 arc minutes apart. That's just my calculation from the plot. So what I did was I looked to see what the angle would be for 2 arc minutes that would cause what baseline do you need to get a half wavelength at this frequency, and it turned out to be 182 meters. Okay, so I had done this back of the envelope calculation before I went to the Western Conference, and I thought, oh, and then so of course I walked. I knew it, but I walked the distance just to check it, to see how far it was, and I went, okay, we can do it. We could look for something that has a response at this distance, because this will determine the resolution of an interferometer. So that was kind of a nice feeling that it was doable. Okay, now what actually happens is that we have those pluses and minuses varying like this, but in the case of the 40-foot where we don't track, we end up with the fringes changing with the composite of the beam width of the 2 antennas that we're using. So the beam width of the 40-foot is 1 degree, and the beam width of the 6-foot dish is 7 degrees or so. And those 2 composite together are going to cause an increase in the fringes and then a decrease in the fringes. And these are the wiggles that I was talking about, where we go plus and minus on the cross power. Okay, now, so at home, on my interferometer at home, where I have a 5.4 meter and 5.8 meter dish separated by 52 meters, I pointed it at the Crab Nebula, let the Crab Nebula go through. These are transit also scopes. I let the Crab Nebula go through the two scopes, and this is an example from about a year ago that I took with the Crab Nebula over a period of 4 days, where you can see the diurnal effect of the Crab Nebula fringes as it goes through the two antennas. So now what happens when there's two sources? Okay, so if you calculate one of the sources, you get fringes, and let's look at this a little bit different now. Let's say that we're driving the baseline. So we're going to go out and get variable baselines. So instead of converting this or looking at this as like a time effect, we're going to look at it as a variable baseline effect. It's one snapshot, but it's what will happen if you move that baseline out along the distance that we've chosen to go. And so that's what the horizontal is. Now I did it in seconds traveled. So this is a seconds traveled, but if we go at a constant speed, it's also the distance along the baseline. Now what happens is the zenith point source, you get this. This is a simulation. So it's just calculated value. You get this frequency, which is increasing. The reason it's increasing is because when we get farther out, that the angular difference is causing more wavelengths at that end due to this congruent angle effect. Now, so we're getting more wavelengths at the high baselines and very low when we have low separation. At near zenith point source, just offset, and I used the two objects that are in Cygnus A as the value for this simulation, and then used all the various times and the travel rate and everything, looks like the other one, but it's got a different frequency. It's got a higher frequency. So you can see that the peaks here, this peak happened a little bit earlier, okay? So what happens is when you have two waves, you know, it's like music, you get the beat note between them. Well, each of these it's a linear process. So each of these sources is producing an output on the cross power and the cross correlator that you could treat as individual outputs, and therefore they could add or subtract. So you're going to end up getting constructive and destructive interference of the two sources in the sky. Now these are two sources that have identical signal strength. Obviously if one of them was low, then you wouldn't see that quite so much. This is the composite of those two simulations that you get. Now there's an aliasing problem in here where I don't take enough points, so you start to see some wiggles in the envelope. But I calculated that at 182 meters, there should be a null where the two signals from the two lobes, radial lobes, cancel. And okay, and so that gave us sort of an idea of, okay, this is what we're going to try to accomplish, is to get something from the cross power lobe, something like that. So this is the system. The truck has the dish in it. The cable goes out and then it comes back. It took a while to figure out kind of a nice way to do that. To be pulling the minimum, you know, I want to coil it up all on one end and then just pull it out, right? So we meandered the cable back, and it turned out it didn't actually pull. You didn't ever have to pull the full length of the cable. So then there's two cavity bandpass filters to make the channels as identical as we can get them. This is the receiver that's in the rack, the down converter, the IF, and then I go into a picoscope 3206 digitizer. It's a gigasample, but I run it at 125 megasamples per second to be slightly over twice the Nyquist of the input bandwidth. The data is transferred over the USB 3.0 with 4 gigabits per second, and then I program in Linux with Ubuntu, and I use a big I use POSIX to get as many threads loaded into the coprocessors. I mean into the parallel processing as possible, the 8 cores. And Picoscope has a very nice API and software, so it's really easy to build systems around their system. You can actually just use their executables, and that's actually what I do. Is I just take their executables that they supply, and then I add the radio astronomy things to it, and it's pretty quick. Actually, I rewrote all the software just for this because I didn't like my previous correlator software. So now you have to correct for the delay, because those waves have to line up with each other, because the intensity of the two sources is changing randomly, if we don't get the delay all the way back to the cross correlator so they're lined up, we're going to have a problem. And the delay accuracy has to be good enough so that when you're looking at that bandwidth, so this is where the bandwidth is important, you're lining the waves up well enough in that bandwidth so that all the frequency components in that bandwidth all can cancel out. Well, if there's a delay on one side or the other, you get a slope. It's a change in phase with respect to frequency across the band, and then the two have a phase shift at certain frequencies, and the cancellation is degraded. Now, we all want as much bandwidth as we can get because of the square root of BT. We want more bandwidth, more wiggles to integrate over a longer period of time. So we always want the bandwidth to be as high as possible. So then there's a trade-off in an interferometer. Well, how good a delay accuracy can you get on this? So fortunately, because we had the cable and the computer, I could get it down so the delay taps were within a certain range. Now, there's a lot of things to correct for in an interferometer, and I am not doing that, okay? There's a lot of simplifications that I've taken in this. So really all it does is delay the signal by what I thought the cable should be. I measured the cable accurately on a network analyzer, and the tests at home that I did with a long coax came out within 10 nanoseconds. So I was pretty thrilled with that. So what happens, now this can get really complicated when we want to measure over a wide angle of the sky. See, I'm only going to talk about two sources that are really close together. But what you really have on there is you got these objects all over the place on the sky at high angles with each other. Well, all of those angles are treated differently in the system, and as the mobile element moves across, you can end up with space delays over the image, and including the effect of the bandwidth, that decorrelate the image. So again, this is something that I have not included in the calculation, but I did do a rough calculation to just show that at this baseline, we would not have a significant effect, and it turned out to be 23 nanoseconds. So I figured, okay, we're going to be spanning delay taps beyond 8 nanoseconds of separation. Now that's something I didn't explain. Okay, that's really important. We don't have to get the delay exact, all right? And there's a trade-off there, because we can search nearby delays. And there's sort of two ways to do that. One is with a fast Fourier transform, where you can essentially, your output will be all of the delays, and you can get everything. I used to do that in some other interferometers I was building in the past. And it's nice because you don't have to worry, you don't have to guess the delays, you just look for some peaks. And then you got to be careful that it's the peak you're actually looking for, so it does have to be pretty close to the delay you're looking for. The second is using time, where you say, no, we're not going to do the FFTs, we're just going to raw multiply the waveforms with delays that are just fixed on one of the channel's input data. And that way you get a limited number of you end up with a limited number of points, but the math can go faster than it could potentially with a full FFT. There's a crossover there. And I thought, well, if I can get the delays estimated pretty fast, I mean pretty closely, I can get more points out of the system. The ideal thing is you want more points because you want to be able to average more points together. Okay, so this was a back of the envelope calculation that showed that things do seem to work over bandwidth and over the image space, although we're not really worried with that too much on that image space. So this is what the fringes, these are called fringes on a cross correlator. When you go up and down like this with plus and minus, where the two elements are interfering with each other, it's called fringes. And I calculated, again, this is simulated data, that as we traveled along the baseline, that at this point, which turns out to be 182 meters, it's not on this slide, I guess it's on another one, that at that point there should be a null due to the two sources that are present from Cygnus A. And then they're going to be a peak. If we went farther, we would get a second peak out here when it reconstructs again. So that turned out to, this is all simulation, but this is what I was thinking, well, okay, if we can do this and get something that looks like this, then, this is a first step. Okay, I talked about these simplifications. I don't do complex, and I don't compensate for for the spatial delay across an image that's, you know, somewhat larger. Now, let me explain how you can make images with this. So, you know how we have these things that go up and down as you move the baseline along, right? So it's going up. That looks a lot. That's two tones. That's like two tones summed together at different frequencies. Well, it turns out that in a theorem, the relationship between the angle on the sky and the correlator fringes that you see along the line, the amplitude of them, are Fourier transform pairs. So like frequency and time. And it kind of makes sense when you think of it, because you say, you know, in the frequency domain, if I have two tones and I take a Fourier transform, I'm going to see something that looks like that. Now these are actually sweeping frequencies, because the object's moving across the sky. This would be two sweepers that are slightly off in frequency, and they're going to have a beat note to them, but they're also going to increase in frequency. So similarly, in the sky, you have sources. These are strong sources that are like received power of these two objects. You take the Fourier transform, and you get the same looking thing. Now, that doesn't apply to only one dimension. You can do that in two dimensions. So what the astronomers do with their interferometers is they create all different baselines in both dimensions. So they fill out a plane of all the values that they want, which are basically data points all along this line, but in two dimensions. That fills out what's called the UV plane. There's also a W, which is the distance to and from the object, which I also didn't include in anything I did here. But it's important because when you're tracking, the W value is changing because the center of the whole array is like a virtual point out there, but as the angle changes, there's a W effect. So, so there's a Fourier transform pair, which is kind of interesting because for us, I mean, we could say, you know, we could start to create some images with this, you know, given a little evolution of the system, right? Okay. So I did some static tests last month with Cassiopeia. So these are test results. This is actually the, quote, first light of the static test only. And I used Cassiopeia. The separation was 110 feet where we placed the antenna out in the field next to the 40-foot dish. And I ran it, and then when Cassiopeia came along, there are the fringes. It's Cassiopeia. Now you see it's very sparse. The data there is missing a lot of points on the sine wave. But it turns out that that's because I didn't know where the peak would be. I had to estimate the delay all the way back through the fiber optic, up to the feed, figure all that out, and then I'd be off. Well, so I didn't want to miss it, because with a 40-foot, if you miss it, you can't point, you know, to get back. So what I did was I increased the scan space of the delay, so I had lots of delays that didn't produce anything useful. They were just zeroed out. And that's what these points are in between. And it was only here, here, and here where the points actually worked. So I just had a crazy idea when I got to this point in time. I went, why don't I just recompile the code and get all the points that I want? So I in between here and here, which is maybe about 1.5 wiggles or something, I modified the code and I only displayed the delay points that are these delay points, which cause these to fill in all along. So that's a much better plot, and we can do much better averaging with it. Okay, so this is the results from 2 a.m. Okay, this was a thrill and a half to see this. This is the continuum of the 40-foot on Cygnus A. So this is a degree beam width at the half-power points. This is proportional to power, perceived power. It's not really calibrated, but it's equivalent to what you see on the chart. Okay, when the chart comes out. And this is the cross power coming out of the cross correlator. And it's a little bit different. What I do is I'm interested really in how big are the wiggles, right? The wiggles are when you see those fringes going up and down, you want to know how high how much they're separated. So what I do is over a period of a certain number of records, which I took with 75 to 175 nanoseconds of delay, I look for the maximum and the minimum of those wiggles, and then I subtract them. So this is actually what you would see. This is sort of the amplitude of the wiggle height, okay, between plus and minus on how high they were wiggling through the cross correlator outputs on each of the delays. Now, what happened was, I was watching it, and actually the truck started right here because I got a little nervous because this was increasing a little bit, but then when I started to see these big numbers, like 50 and 60, I went, oh, we're getting a lot of correlation. Most of the time you get numbers like this, down, you know, that's what the correlator does. Actually, the antenna was disconnected at this point. So this is sort of correlator noise. This is actually with the two antennas connected, but outside the beamwidth of Cygnus A. And so when I saw that, I went, oh, we got to get going, because if we don't get the truck moving, the whole thing's going to be displaced into this region over here, which I didn't want. Okay, so we got lucky. And I just said, okay, go. I alerted Tom. Tom alerted the truck, and we all bucket brigade thing. And the truck left here, and then we saw these correlated fringes. Now, when these started to occur, I thought, oh, wow, what's going on there? You know, thinking something's broken, thinking the antenna shifted or something like that. But it kept decreasing. Well, and then the software crash, which this is kind of obnoxious, but it lasted for about 10 seconds. And I said, no, I'm not going to. Okay, so I restarted it. So something weird happened right in here. This point, using numbers that were calculated or measured on the truck, was at 186 meters. That point right there. Well, the null is actually over here, which says that, I mean, we could do some very rough, like very, you know, kind of speculative with a lot of assumptions, calculations, and say, the objects are a little closer than 2 arc minutes together at 1400 megahertz. The peak of them, if they are equal in strength. Now, the other thing that's interesting about this is that these peaks, they go out to a really deep null, which says that the two peaks are probably about the same amplitude. So you could actually take what you see on the strip chart, and from this you could say, well, let's draw two peaks, let's draw them, and let's show them at a 30th of a degree, beamwidth, but we don't know what other information there might be in there, and let's make them at the same amplitude. So suddenly we now have a plot which has a 30th of a degree resolution of 2 points while we're pointing at Cygnus A. Okay, which kind of says, oh, okay, well, this is new information. You know, I mean, for us, right? For me it is. I've never seen Cygnus A with anything I've done with, you know, resolution of this. And then this one was a little bit lower. It could be because of the difference in this. I just put this plot together an hour ago, so I haven't looked at it a lot. But this might be because we're just lower on the peak. And with some calculations, I can compensate this. This is uncompensated for the amount of the beam, the effect on the beam. This could bring this up. And it would be kind of interesting to see if the two peaks are equal. They should be. And then we can also get a better estimate of the null, because this high point will cause this to come down a little bit. This will go maybe down a little bit. It might be about equal. So this could be the ratio between the two lobes of Cygnus. Okay. And then the truck stopped here. This was the 610 foot. This was the 110 foot point. And then the cable was disconnected a little while later. I definitely want to just ask everyone who was at 2 a.m. to stand up. I'd like to thank you all. Just yeah, there was a wonderful group of people who. And thank you all. It was a ton of fun. I really enjoyed that. So, I do just want to talk about the future a little bit. I'm thinking about. I've got two of these locked oscillators. They're GPS locked oscillators running at home, and I'm amazed that when the two antennas are this far apart, that the two oscillators track with a nanosecond of noise with respect to each other, which means delay and frequency up to high frequencies can be compensated for with two separate operating receivers. Now, so there's some hope that there's a possibility that we could put more stuff in the truck and actually just drive the whole facility in 2 dimensions in the 4 minutes we can't go very far, but maybe we could track with a 20 meter. and use that. But so there's some thought, you know, as this goes on, and if people are interested, you know, and want to contribute to it, we could add, you know, make it more complex, and we've got to get permission to put all that RFI generating stuff inside of shielded boxes. But it could lead to two-dimensional images. So, okay, yeah. Yep. Oh,
Yeah, I said, did you have to pay attention to what your velocity was as you're driving along?
Yes.
And make sure that your velocity was had an exact number at some point?
yeah, Sid drove. I calculated 2 miles an hour. And then we also calculated that if we went 30 seconds between, oh, there's a whole bunch of flags I didn't mention, but between the 40 foot and the 140 foot, every 100 feet, there's a pole with an orange duct tape flag on it that is very visible. I think it's visible, right, at night with a flashlight. And that time between those 100-foot flags turned out to be 30 seconds, roughly, plus or minus. So we got records of the actual time that occurred, which meant that I could calibrate the horizontal axis of the baseline, which is the baseline is what we need to know, but we get it from time. And that was critical, yes.
2 miles an hour.
2 miles an hour. And now you could say, well, what's the problem there? You know, well, it just means that our horizontal axis is going to get, you know, squished around like this. But if we tried to take an image, it would mean that the whole image would be kind of like contorted a little bit. And we wouldn't want that. So, of course, in really serious interferometers where there's, you know, very extensive work going, they got this all down to, you know, millimeters of distances. Okay, yeah. Yeah.
Do big interferometers like the VLA, do they use drift scan, or how do they do
They
this?
track, everything tracks.
Okay.
Yeah, so almost, that's one of the things that's kind of strange about this is that nobody I mean, I don't know how many interferometers people try to go with static one element, right? Because, you know, you don't get to look very long, and so many interferometers rely on the Earth's rotation to give you that baseline change, right? So as the Earth rotates, the baseline is effectively, when you look at that object, decreasing as you're going toward the horizon. So that's how they actually get the baseline to change over on very long baselines, and even on shorter ones, like in the VLA. So it's essential that they track. And that's almost the assumption that's always made. So this is significantly different. Yeah.
Since you mentioned tracking, what kind of tracking accuracy do you think you need to have to do valid tracking?
Oh, that's a great question. I'm gonna just throw this out there, but I don't know all the details to it. But I would just say that if you're within the beam width and you've got like a reasonable amount of, you know, towards the peak, like within a 1/10 of a beam width or maybe a 20th of a beam width, the variation you get across that peak is so small that the noise in the correlator, if you can get it down below the noise of the correlator, which depends on the signal to noise ratio of the object you're looking at, then it's probably okay. There's another effect, which is the phase. The phase of an antenna varies across its pointing direction. So that effect, I haven't calculated that and figured that out. But it probably you'd want it to be within a
I've
fraction
seen
of
some
a beam.
numbers of going back to what we call precision orientation of microwave antennas.
Mhm.
I think we were down to like less than a 1/10 of a degree we had to get to
Mhm. Yeah.
get the phase relationship right.
I think so. I think that's important. Yeah. Okay. Okay, thanks again to everybody who helped. That was a lot of fun.